Alright, in this video I'm going to go ahead and continue to prove that e to the I theta is in fact the cosine of theta plus I sine theta. That is the Euler form of a complex number. And to do that, we're going to need some things from previous math classes. One of them is we're going to need the series expansion for the cosine function. The cosine of x is x to the 0 power over 0 factorial minus, my fault, minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so forth. The alternating sign between plus and minus is what keeps the cosine bounded so that it doesn't go off to infinity. The other thing to note about it is that you only have even powers of x. This ensures that if you change x to minus x, when you put that minus sign and take it to even powers, the minus sign falls away. So the cosine of minus x is equal to the cosine of x. That is, you have an even function. We also need to know the series expansion for sine. This is x to the 1st over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and again, so forth. Again, the alternating sign, keeping the sine function bounded. This time you have odd powers of x. So because it's odd powers, if you change this to minus x, it will put a minus sign on every term. This means that sine of minus x is minus the sine of x. This property is the property of an odd function, and you can see that because it has only odd power terms. The last one that we need to remember from previous courses is the expansion for the exponential. The exponential has this expansion, x to the 0, which is 1, over 0 factorial, which is 1, plus x to the 1st over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4 over 4 factorial, and so forth. Because there is not an alternating sign, if x is a real number, this thing blows up when x gets large. Now, this is neither an even nor an odd function. It has both even powers of x and it has odd powers of x. It does show one of the things that we know from mathematics, that any function can be represented as the sum of an even and an odd function. Now those things, these three, represent definitions in essence of the cosine, the sine, and the exponential, and this is what calculators actually use to compute these things. It's important to know that in these expansions that this value, this x, cannot have units. So the argument of an exponential must always be unitless. The argument of a sine function must be unitless. The unitless quantity that is used for an angle is called the radian. So this thing requires x to be in radians. The same thing is true for cosine. I'm going to use these now to derive this expression where x is a complex, I theta, rather than just a number like 4. So let's do that. Let's start with using our definition here, e to the I theta. Now that means I should put I theta and raise it to the 0 power over 0 factorial, and I theta to the 1 over 1 factorial, I theta squared over 2 factorial, I theta cubed over 3 factorial, and so on and so forth. Now, I'm going to split the thing into two parts. I'm going to put all of the even powers together, and I'm going to put all the odd powers together. So I'm just going to rearrange terms. e to the I theta is equal to I theta to the 0 power over 0 factorial plus I theta squared over 2 factorial plus I theta 4 over 4 factorial, and so on. And I also have plus I theta to the 1 over 1 factorial I theta cubed over 3 factorial, and so forth with the odd powers. Remember some things. Remember that I to the 0 is 1, I squared is minus 1, I to the 4th power is 1, I to the 6th is minus 1, and so on. Now, given that fact, I want to change what I did just a little bit. For this one, I to the 0 is simply 1, and I get theta to the 0 over 0 factorial. So this is theta to the 0 over 0 factorial. I squared is minus 1. So I get minus theta squared over 2 factorial. I to the 4th is minus 1 times minus 1, which is 1. So I get plus theta to the 4 over 4 factorial, and so on and so forth. With the odd terms, I'm going to factor out an I. So if I take an I out here, then I have theta to the 1. There's no I. I've already pulled the I out, over 1 factorial. So it's to the first over 1 factorial. I had I cubed. Well, I took one of the i's out. That leaves an I squared. I squared is minus 1. So I get minus theta squared, theta cubed over 3 factorial. The next term would be I to the 5th. But I took out an I, so I have I to the 4th. I to the 4th would be a plus 1. So I'd get a plus 1, and then I would get theta to the 5th over 5 factorial. Now I look at this, and I say, hey, hold it. If I look at that term, that's exactly the same as this, except instead of x, I have theta. So this first parentheses happens to be, the wrong one. Go back up one higher. This 0 over 0 factorial minus x squared over 2 factorial, that term and what's in this parentheses are exactly the same, except instead of x, I have theta. Show that one more time. So instead of x, I have theta. So this is cosine theta. So this right here, by comparison with our expansions, this is cosine theta. This term here, I have odd powers, plus, minus, plus, minus. When I look at that, that is the sine, except instead of x, I have theta. So this right here is sine theta. So e to the I theta is cosine theta plus I sine theta. And so I've proved that what this is this. And so if that's 1 and that's theta in the complex plane, this is sine theta, this is cosine theta, this is the real, this is the I, the imaginary. So I sine, that's this side. This side is this. You add this side plus that side, and you get this arrow. And that arrow represents e to the I theta. So e to the I theta represents an arrow. Now, that theta doesn't have to be fixed. It could be omega t, in which case this arrow could be running around like this. in circular motion. And we'll find that useful when we deal with harmonic oscillatory motion. The Euler form is extremely useful when you multiply or divide complex numbers. Example, you want to find a times b. A times b is 5ei pi over 2 times 2ei pi over 4. So we're talking about taking an arrow like this and an arrow like this, where this is pi over 4, and multiplying those two arrows together. And what do we get? We get 5 times 2 is 10. But when you add exponents, or you multiply e to the I and e to the I pi over 4, that's just adding exponents. So this is pi over 4 plus pi over 2. So the result is another arrow whose length is 10, but whose angle here is pi over 2 plus pi over 4. So when you multiply complex numbers in Euler form, you multiply the lengths and you add the arrows. You add the angles. This has lots of applications, including finding the roots of an equation, which I'll talk about in another video.